In this lecture, we're going to discuss training and tuning deep neural networks. So let's begin by just talking about how deep neural networks are implemented in R. There are several packages that can be used for training deep neural networks. Neural net is probably the most basic in the sense that it's the easiest to use, but also correspondingly has the fewest kind of additional features. And this is used on homework assignment 4. Or at least it's recommended to be done this way. A very powerful neural network package is called Keras. Okay, and then the textbook uses this. In particular, all the examples done in chapter 13 are using Keras, using, for instance, the MNIST dataset. But there's an issue here. Most of the code that we've seen in the textbook already, we could run just basically by copy pasting. But to use Keras, you need a setup called TensorFlow, and which comes from Python. And so you need to have all of this set up, in particular, in the right way. So unlike previous chapters, simply copy pasting the code from chapter 13 and trying to run it in R is probably not going to work unless you have all of this stuff already set up. Okay. So if you do know how to use Keras, I mean, you feel free to do so. But neural net is probably your best bet if you're simply trying to implement a reasonably simple neural net package in assignment 4, and also if you think about using a neural net on your final project. And there are several others, and you're welcome, of course, to explore those at your own leisure. So how are we going to build a neural network in R or otherwise? First, we need to talk about data prep. Okay. So feed forward, and this is true of other types as well, but feed forward deep neural networks, the basic kind that we're discussing here, require, the most important part of data prep here is that they require feature inputs to be numeric. So the idea is, even with categorical features, they need to be fed into some sort of net input function and multiplied by weights. Okay. So in particular, categorical features must be numerically encoded. Okay, so this is the most basic issue regarding training neural network, or training neural networks is the data. But there's another issue that, besides being numerical. So further, because of the whole idea of weighting and net input and activation functions, deep neural networks are very sensitive to the scale of the feature values. So in other words, feature values of lots of different types are going to that's going to have an effect on the model. So it's important to normalize the feature values in some way, so that they're all in some sense being measured on the same scale. So there's different possibilities. One way to do this is standardizing. So using z-scores, making and converting them to a standard normal distribution. Another one is what's called max-min normalization. This is going to be preferable to standardizing in situations such as, for instance, doing binary classification. You'll see this on assignment 4, that you'll want to use max-min normalization there. And there are others, etc. Okay. So just to be very explicit about what I just said, so suppose we are doing binary classification. Okay. So in a binary classification problem, target values are coded with zeros and ones, classically at least. If we standardize, well, then we recenter the mean at 0. So in effect, we change to -1, +1, or say -c, +c, if after changing the standard deviation as well, it changes the values for some c. Okay, but the idea is now we no longer have zeros and ones. We have some positive value and it's negative as the 2. And you might say that, well, what's wrong with that? Then it becomes tricky, for instance, when running on a testing set and looking at, say, testing it and forming, say, a confusion matrix. So in this case, another method, such as the one already mentioned, max-min normalization, may be preferable. Okay, so keep this in mind, that when scale, we need to have the data be on the same scale, but the choice of normalization to put all the data on the same scale can be something that can matter. Okay, so now let's talk about building the initial model. The model that we're going to tune. Oops. All right. So first we want to do is initiate the feed forward DNN architecture. Specifically, we begin by adding some dense, what we call dense layers. What we mean by this, so dense, or the other term that gets used is fully connected, means that all nodes in each successive layer are connected. So at each hidden layer, a node sends its output to every node at the next hidden layer. So I'm going to follow the example in the text, just at least in terms of explaining how you might go about doing this, even if we're not actually necessarily going to implement it. And you can go back to the text and look through the details if you like. So what we're going to work with, not surprisingly, is the MNIST example that we've been talking about as we've gone through this. So we're going to create 2 hidden layers. first has 128 nodes. And the second has 64 nodes. And then we're going to create an output layer with 10 nodes. And of course, this is because we're doing a multinomial classification problem. Those nodes are the digits 0 through 9, the possible predictions. Okay. And then what we do is connect all 128 nodes in the first layer to the 64 nodes in the second. So for each node in the first layer, there are going to be 64 output branches coming off of it, each one being sent to a node at the next hidden layer. And then similarly, the 64 nodes at the second layer are each going to send a branch to the 10 different hidden nodes. Or sorry, the 10 different output nodes at the output layer. Okay. So typically, the first hidden layer needs to know the number of input layers. In other words, features. But then nicely, we don't actually have to tell the other hidden layers what's going on. So successive hidden layers are able to dynamically, so in other words, as the model trains on their own, interpret the number of expected inputs, how many signals they expect to have coming in, based on the previous layer. Okay, so when we said at the start, we're going to initiate the deep neural network architecture. Remember, the basics of the architecture are the number of hidden layers and nodes at each layer, and the activation functions. So now let's talk about activation. How are we going to do activation in this set? Okay, so we can specify, if we like, which activation function to use at each hidden layer. So in our example, so just as a reminder, every time I'll write this, just keep writing it down. The example is we're going to keep using is MNIST. So the hidden layers, both hidden layers here, use the rectified linear unit, ReLU, for activation. And the output layer uses softmax. Because remember, softmax is the sort of activation function of choice for multinomial, for the output activation in a multinomial classification problem. So now we need to specify the backpropagation algorithm that the deep neural network is going to use to learn, to make improvements on its predictions over each forward pass. Okay, so in the backpropagation options, we can specify, as discussed at the end of class last time, there's essentially two aspects, core aspects to the backpropagation algorithm. The loss function or functions that we want to use to measure model performance, and the optimizer. And remember that the optimizer is the specific version of the mini batch stochastic gradient descent algorithm. So that's the minimum that we can specify if we want. The other things we can specify are other metrics such as accuracy, in addition to the loss functions. Okay. So this allows us to set up the basic model. Next, we consider model training. So how are we going to train the deep neural network on the data? So we feed the base model into what we're going to call a training function. So in the Curas package, this is referred to as fit. Okay, so we fit into a training function with the training data and specify, if we want, various options. Okay. Now, there are many options. How many, of course, depends on what kind of package we're talking about and how much, how rich it is. But here are a few. And then these are the syntax for Curas so that you can follow along in the book. But these kind of options will be available in NeuralNet and other packages as well, sometimes with slightly different syntax or names. Okay, the first is batch size. And what this is this is the size of the training samples selected at each node for the mini batch stochastic gradient descent. So remember, we pick a batch of, hence the name batch size. Take a batch of sample data, and we run it through the algorithm, and then go back through the mini batch gradient descent algorithm in the back propagation. And then we choose another one, and so on. So batch sizes are usually, as it turns out, a power of 2. For computational reasons, and can often range from as low as 1, so simply one observation, to several hundred. Although, like a lot of other machine learning parameters, these are kind of typical values, but anything really can be used if desired. The second are what are called epochs. Okay. So what do we mean by an epoch? What this is the name for is the number of times the algorithm, as it's training, sees the entire data set. So of course, it may take many batches to achieve an epoch. So the idea then is that we say an epoch is completed if every data point has been seen. At which case, we may simply start over again. We'll start going back through data points. Our next option we'll talk about is what's called validation split. And the idea is, well, like any other model, we're going to want to validate as we go. So this is just some percentage, x, y% of the data, or x and y, or whatever numbers we want them to be, is held out of the training sample to use for validation. So in other words, out of sample error estimation as we train the model. Okay, so let's look at, as always, the MNIST example. And let's see what happens on a model run. So let's take a look at the following image. So in the image, we have both the loss function and accuracy being measured here. The training data is indicated in orange, and the validation data is being indicated in sort of teal blue. And what do we see? Well, notice that the horizontal axis is the number of epochs. So in some sense, we're looking at how long is it taking to train this model. And we see that the performance improves rapidly in the training over the first few epochs. So we see a reduction in loss function, increased accuracy. The model performance in terms of the validation data is roughly optimized in the sort of 6 to 10 epoch range. And then once we pass 10 epochs, what we see is the model overfits to the training data. And the way we can see that is looking at the validation data. So once we're about past 10, the accuracy is basically flat, whereas we see a slight increase in the loss function. And that increase actually gets a little bit worse as we pass, say, 15 epochs. It actually starts to increase more rapidly. So that, of course, recall that one of the nice visual ways to see overfitting is to look at, well, how big is the discrepancy, the gap between the training data and the validation data? And then so we see that at around 10 epochs, the training data and the validation data are reasonably close together, but also both relatively low. And then from then on, the gap between them grows very quickly and gets quite wide. And in particular, the validation loss function measurement increases. We similarly see the same thing in the accuracy. Okay, so this is what happens when we sort of run a basic training run on this data, on the MNIST data, and build a neural network. And so just as a reminder, so this is from the text, and this is all done in QRS. So going back, now let's consider model tuning. So here we've trained a basic model. How do we tune it? What are the hyperparameters that we can tune? So of course, what we want to do, the point of model tuning, is we want to improve over just a base deep neural network model performance by tuning the hyperparameters. So tuning various hyperparameters. Okay. So we'll point out now that this is there's a lot here. Okay. There are many hyperparameters. We're only going to talk about a few of them. And many ways to tune the deep neural network. And so we're going to lay out a strategy for tuning that gives at least some idea what a typical tuning process might follow. We're not going to be as exacting about this as we were, say, with gradient boosting, because there's a lot more to say that we're going to leave out. Okay, so there's lots of choices of what to tune. There's lots of ways to tune it. Moreover, tuning deep neural networks tends to be very computationally intensive. So this can be seen if you look through the textbook and read descriptions of the various grid searches that are going on and how many model assessments they're able to make and how long it takes. So for instance, they run for 3 hours and it only assesses some small fraction of the possible models, for instance. So just to make a general comment about this, so the runtime for deep neural networks requires, so I'm going to use big O notation, which is basically just saying order of NPML, so a product, a 4 power essentially, a product of 4 terms operations. Where, what are these 4 letters in this? Capital N is the number of observations. P is the number of features. M is the number of hidden nodes. So not just hidden layers, but the total number of hidden nodes. And L is the number of epochs. So then computationally, this grows very quickly. So this requires extensive computing power to be feasible. So deep neural networks as a machine learning technique only really came into their own and came to prominence once there was a large level of availability for high performance CPUs and GPUs and parallel clusters and so on. The ideas behind deep neural networks were known prior to that, but to actually implement them in a way where they had a real advantage over shallow machine learning methods requires a lot of computational power. Okay. So as mentioned, we're not going to go through the kind of the full formalities of how you might tune deep neural networks. What we'll talk about here is what a sort of typical, in some sense, DNN tuning process follows in terms of general steps. So a typical DNN, so tuning process follows these general basic steps with lots of iterations. So in other words, repeating many of these and this process many times. Lots of iterations of them. Okay. So the rough outline is you start by you adjust what's called model capacity, and we'll explain what that means in a moment. Oh, my pen wasn't working. I'll fix that. There we go. Next, you add what we call batch normalization. So all these terms are going to be explained. Then we add regularization. This means the same thing as it did before, just in the context of regularization in the context of neural networks. But in particular, what we talked about in chapter 12 with gradient boosting essentially works here too. And then we adjust the learning rate. And learning rate means something, of course, very similar to what it did before as well. Okay. So let's go through these and explain what they are and how they work. So what do we mean by model capacity? So this refers to essentially the number of layers and the number of nodes. And so we take these together these form what we call model capacity. So higher model capacity results in more of what we might call, thinking about this again as being some sort of artificial brain, memorization capacity. It allows the deep neural network to remember more. It gives it a larger memory. Okay. So there's good and bad aspects of bumping up the model capacity. So the good part of this is it allows the deep neural network to learn more complexity, so more complex aspects, so complexity, patterns, relationships, etc. And the bad part, well, leads to overfitting. And so there's no obvious, there's no kind of hard rules here, like a lot of other machine learning tuning. The the basic rule of thumb that you might go with is if increasing model capacity leads to lowering validation error, then do it. Otherwise, of course, then stop. If you're getting more validation error as you increase model capacity, this is a sign that you're overfitting. So here's an example from the MNIST data. And we'll keep coming back to this. So notice here that across the top row tells us the number of hidden layers, 1, 2, and 3. And then the column, the right-hand column says small, medium, and large. And this is just referring to the number of nodes at each hidden layer. As before, the red curve is the training error, and the blue curve is the validation error. And so we see that for large levels of model capacity, so the bottom the bottom row and corner, so the kind of bottom right, we're getting a much larger gap between the training and validation errors. And in particular, the minimum validation error is actually higher, say, for the large capacity 3-layer model than for, say, the smallest validation error we see here, minimum error, which is for the large number of nodes 1-layer model. So this is something then to keep in mind. We're not just looking for the lowest validation error, but also, for instance, we're looking for, is there a large gap between, say, the validation error and the testing error, which is one of our signs of overfitting. So next, we consider what we call batch normalization. Okay, so the idea here is that at the start we normalized our data so that all the input data was the same. But then we might want to do is normalize the data, normalize the data after every transformation performed by the deep neural network. And in particular, this helps with deeper networks. So as we go deeper and deeper into a network, the data coming from the different nodes, if we haven't normalized, maybe look more and more different. And in particular, the observation when we have deeper networks is that this batch normalization reduces overfitting. And it helps minimize validation loss more quickly. So here is an example of what this looks like with the MNIST example. So here what we're looking at is validation error, and the red curves now are both curves are validation error. The red curve is without batch normalization, and then the teal blue curve is with batch normalization. And so now we see that with batch normalization, a deep model, the 3-layer model with a large number of nodes at each hidden layer, is actually in some respect performing the best. It has the minimum validation error compared to before. So we see then in particular that with a large number of hidden layers and large number of nodes, adding batch normalization has a bigger effect. So we see that in sort of on the bottom, on the right-hand column, the bottom 2 entries, we see decent sized gaps between the validation errors with and without batch normalization. Whereas for the ones, the more shallow models with networks with one or two hidden layers, there's not as much of a difference, other than perhaps at the very bottom with the large capacity, large number of nodes. The third aspect to tuning is regularization. So regularization here is the same idea, so we won't repeat all of it again, as for regression in chapter 6, and when we introduced regularization for gradient boosting machines in chapter 12 as a hyperparameter. So there are two basic approaches. And they're actually what we talked about for gradient boosting. So the first approach is, as not too surprisingly, add an L1 and or L2 penalty parameter. And this is the same as before, the same idea. And the second possibility is to use the idea of dropout, which we introduced in the context of gradient boosting, where we dropped some number of trees, randomly dropped some percentage of the trees out from the boosting process at each step. Now, what does that mean here? That sounded like it was fairly tree specific. But what it means in this context, so for deep neural networks, dropout means to randomly drop some outputs in a hidden layer. So the output's going to, from some hidden layer, we want to drop the outputs going to the next hidden layer. And the way that this is done is it randomly sets the corresponding weights to 0. So in other words, it will send a signal of 0 to the next nodes that it's coming from it. So if we add dropout in the MNIST example, we see first here we have a baseline, and we see a large gap between the training error and validation error, and a large minimum validation error. If we add the baseline and batch normalization, we take the baseline and add batch normalization, we see a lowered validation error. So notice in this case, what we're working with was the one that was the large 3-layer network. And we saw this already. We see a lower minimum validation error and less of a gap between the training and the validation. Finally, if we take the baseline model, so just to recall one more time, this is the large 3-layer model, large capacity 3-layer model. We add batch normalization and we add dropout. We get an even lower minimum validation error and much less overfitting. Now, the training and validation errors are much closer together. So this indicates that this is doing a pretty good job of training this model. Okay. Finally, there's the learning rate. And the idea is, well, remember that backpropagation uses a stochastic gradient descent algorithm. And so learning rate is one of the typical parameters in a gradient descent algorithm. So there is a learning rate in the optimizer, so in other words, the mini batch stochastic gradient descent, and this can be tuned. So the same considerations for tuning learning rate as for gradient boosting apply here. Namely, that if the learning rate is too large, the algorithm may jump over a global minimum. If it's too small, it may take too long to train and or not reach that global minimum. So finally, here is a graphic showing in the MNIST example what happens if we tune the learning rate. Oh, so wrong one. No, this is okay. Oh, yeah, this is right. So what happens here? No, that's not the right file, is it? Sorry, I'm not actually sure. I think I have the wrong image loaded, but I don't have the other one available. Anyway, you can take a look in the text. Sorry about that, and take a look at what happens when you, in terms of tuning the learning rate.